So in the last video we talked about charge and how it's just some property that some things have. We talked about the two different types of charges, positive and negative, and a really brief intro to how they interact with each other. So we're going to look today a little more deeply at those interactions and talk about electric forces. So there's some kind of force that's associated with things that have charge. If it has an overall net charge, it's going to have an overall net force, whether it's exerting it on another object or having it exerted on itself. So electric force, it comes up in all kinds of places. Anything that has batteries, anything you have to plug into the wall, but that's not all, and that stuff is more what we'll talk about when we get to our next unit, which is going to deal with circuits. What we're going to look at now is more about just stationary charges. And a lot of what we looked at earlier this year, and even pretty much all the stuff last year, comes from electric charges. So in the mechanics part of physics, you talked a lot about things that touch each other, car crashes, handshakes, anything like that. So those forces actually come from electric forces. The atoms of the two objects, whether it be two cars, two hands, they never actually touch each other. So in your whole life, your atoms have never touched the atoms of anything else. It kind of makes you feel really lonely, doesn't it? So you can't ever touch anything. It actually comes from, those forces you feel comes from the atoms repelling the atoms of the other object. So this electric force, it's kind of analogous to what you studied last year, gravitational forces. Electric force is analogous to gravitational force. So if you remember, gravitational force depended on the size of two masses, and it depended inversely on the square of the distance that separated them. When we talk about electric forces, specifically Coulomb's law, it's almost the same. The equation that we have here for Coulomb's law, Fe, electric force, is equal to K Q1 Q2 over R squared. So in this equation, the Q1 and the Q2 are what we use to represent the two charges that we're looking at the interaction between. So those are the actual charges of those two particles. R we have representing the distance between them, so down here in the denominator. And that K is just some constant. When we're talking about electricity, K stands for Coulomb's constant. And for what we need to know, when you do your math, you can pretty much use 9 times 10 to the 9th. In reality, it's a little less than 9, but we'll be okay to use 9 here. And units for that will look like coulombs squared per Newton, not right, Newton times coulomb squared divided by okay, here we go. 9 times 10 to the 9 newtons times meter squared per coulomb squared. I was looking a little bit ahead and got myself a little confused. So Coulomb's constant, 9 times 10 to the 9 newtons meter squared per coulomb squared. Where does K come from? Well, Coulomb's constant we can express in some other fundamental constants. Here, permittivity of free space, epsilon 0. So that epsilon 0 has a value of 8.85 times 10 to the minus 12 coulombs squared per newtons times meters squared. So if we wanted to express Coulomb's constant in those terms, K is equal to 1 over 4 pi epsilon 0. So if this was anything that would come up on a test, you do have the value for K given on the equation sheet. Permittivity of free space would be on the equation sheet. So really this isn't something you'd have to memorize. It'll always be there for you. But I'm sure you'll get used to using 9 times 10 to the minus 9. Fun story. If you take this fraction that we set up here for Coulomb's constant, it'd be 1 over 4 pi epsilon 0 oofpez. When I was in college, my professor would write oofpez a lot, and it was so catchy it ended up being my screen name for pretty much everything. Oofpez or IR oofpez. If you ever run into that name anywhere, it's probably me. Coulomb's law to try and find the force that exists between two charged particles. So let's start with these two, one with a positive charge, so positive Q, and the other with a negative charge, negative Q. And their distance r apart. If the distance between them is doubled, and the charge of one of the particles is doubled, how is that going to affect the overall electric force between them? So according to Coulomb's law, the electric force between the two particles at first is just K Q1, which here our Q1 is positive Q. Oh, I'm still in subscripts. Positive Q times negative Q, and that is going to be over R squared. So we can take this math, simplify it a little bit to find that the initial force between these two is just negative K Q squared divided by R squared. So that's our initial force, negative KQ squared over R squared. So now we want to double one of these charges and double the value of R. So it doesn't specify which one we're doubling. Let's pick whichever one we want. So let's double this positive one first. K times 2Q times negative Q. And our distance goes to 2R. So let's do the same thing we did in the last one. Let's go through and clean that up a little bit so we can compare them. We have negative K. Q is still squared. And that's going to be over 2R squared. So we had a 2 on top, 2 squared on the bottom. So it'd be 2 over 4 reduces to 1/2. So we made all those changes. We doubled the charge of one of the particles and doubled the distance. So our overall force is actually divided by half. So in reality, we're dividing the force by 4 by doubling the distance. It's squared in the bottom. So overall, electric force is half as strong as before. The only thing different between these is the 2 there in the denominator. Example considers a really simple case. Obviously there are more than 2 things in the entire universe, so they all have this simultaneous interaction on each other. That's where we look at the idea of superposition. If you're pretty good with vectors, then this won't really be anything too intimidating for you. So we're trying to look at the net force on some particle as a vector sum of all the other forces that are acting on it. So if we have a bunch of charged particles, Q1, Q2, Q3, we could look at the net force on Q1. The net force is going to have some part contributed by Q2, and it'll have some other part contributed by Q3. If we want to make this really general for some system that has some number n of particles, then we could say that the overall total net electric force acting on charge 1, so F1, is equal to whatever the force that charge 2 exerts on charge 1, plus whatever force charge 3 exerts on charge 1, plus 4, plus 5, plus 6, all the way until you get up to whatever your last charge is. So the last charge exerts some force on charge 1. Let's say we have 4 charges, all the same size. They can be all the same sign if you want to. How could you set those charges up so that some Q1 would experience no net force? If we arrange our charged particles with one in the center and the other forming a triangle around it, the center one would actually experience no net charge. So this one above it pushes it straight down. You can see that force vector here. This charge pushes it to the upper left. This charge pushes it to the upper right. Overall, it's going to have 0 net charge. The horizontal components of the net force cancel out, and the vertical components of the net force cancel out. Let's try it again a little more mathematically. Oh, no, not mathematically. We're not throwing in numbers yet. Let's try it again in this example. We have this figure above at point A, a positive Q, a distance r away from point B, where we have another positive Q, and another r away to a negative Q at point C here. So in this figure, we want to figure out what is the direction of the force that's acting on particle A. And C, since A is a positive Q, C is a negative Q, that's going to be an attractive force. So A is going to want to get pulled down towards C. That arrow is not going the right way at all. Come on, Adobe. So A wants to go towards C. What's going to happen between A and B? A is a positive Q. B is also a positive Q. That means that B is going to repel A. So do the same thing here so we can see that. So we have one vector pulling straight down. We have another vector pushing off to the left here. Remember, when you add vectors, you want to do it tip to tail. So we have our downward vector here, and we're going to add to that the vector that goes off to the left. So where did we end up? We started here, went down and across. We ended right over here. Oh man. So that overall net force, what is the direction of the net force acting on particle A? It's going to be going down and to the left at the same time. It's going to do what both of those other two vectors are doing, but at the same time. Since Adobe is so terrible with arrows, here's a little bit better picture. We can see charge A right here. The force from B onto A pushes off to the left. The force from C to A, remember it's attractive, so A is going to get pulled towards it. When we put them together, you can see these dotted lines here